and welcome to a lecture on a quick review of some assumptions of t-test and a new topic this week, ANOVA. We're going to be comparing means between more than two groups, which is called analysis of variance. If you recall, t-test, which compared means, looked at two groups, two samples, and analysis of variance is for looking at more than two groups. So, moving right on. As I said, we're going to be doing some clarifications on the t-test from some issues that students came up with from last week's work. First of all, what does a negative what does a negative t-value mean? Well, remember that with a t-test, you're measuring the difference in means between group 1 and group 2. You can only measure two groups. So it comes out to mean 1 minus mean 2. All right, so a negative t-value merely indicates that the mean in group 1 is smaller than the mean in group 2. So if you're taking if you're deducting or subtracting M2 from M1 and M1 is smaller, you're going to get a negative number. If you were to check in the t-distribution table, you would use the absolute value of t, in other words, without a sign. The other thing is that people asked why SPSS, they could not find a one-tailed test when using t-test, just the two-tailed test. Well, there is no one-tailed test in SPSS, and so two-tailed, as you recall, gives no prediction about the direction of the results. We're not making a prediction about the direction of the results. We don't know which will be greater than the other. All right? Whereas a one-tailed test is pointing at either the left or the right tail of the curve, and they are in that case making a prediction of which tail your results are going to be under, which group will have the highest mean. Okay, we could obtain a one-tailed probability, however, by dividing the two-tailed statistic by 2, and that just gives us the probability. And this is a illustration of one-tailed test versus a two-tailed test, and I just want to get my pen down here. There we go. And so let's just go ahead and split. Here's the curve, and let's just split this curve down the middle. Well, that's not precisely down the middle, as you can see, but here's my right tail, and here's my left tail. Okay, and so with a one-tailed test, we're going to predict whether we're going in this direction or in this direction. Okay, so with a two-tailed test, we have to split the probability across both of those tails. So there, we have 0.025 at each end. So there's 0.025 here and 0.025 here to get what? To get that alpha of 0.05, which is what we don't want to go over. Okay. So one tail probability is only in one tail. So your p-value can be slightly larger and still be significant. Okay? And the downfall is that if you predict in the wrong direction, let's say that I'm predicting with a one-tailed test under this tail and it goes under this tail, I'll never know because we won't detect any effect that does exist in the data. Okay? So let's pop over to the next thing that gave people some heartburn, and that was the Levine's test, or the Fmax test. The null hypothesis for this test is always the same, that there's no relationship or no difference in means. Okay, you fail to reject the null hypothesis when p is greater than 0.05 in general, you don't want to accept the null hypothesis. This is in general when we're dealing with regular probabilities. You'd like to show that there is a significant association between your variables. In the Levene's test, it's different. All right, Levene is the only test for which we do want the null hypothesis to be true. And why that is because the null hypothesis equals no difference in the variances between your groups, and we want the variance to be homogeneous. We want it to be the same in both groups, or else we violate the assumption of homogeneity, okay? And that's what we don't want to do. So we want that null hypothesis to be true. And the other thing that we talked about was the phi, or the strength association, okay? And what does a negative phi mean? Well, you have to know a little bit about symmetricalness, and it's symmetry, it's symmetrical. Phi is a symmetrical measure. It means it makes no difference which is the independent variable. Phi tends to underestimate or understate asymmetric relationships. So note, however, that some computer packages, such as Stata, Systat, and others other than SPSS, use a special formula for phi in 2x2 tables, so that phi varies from -1 to +1, allowing it to indicate a negative relationship, okay, when you're using a dichotomous ordinal variable. And however, phi is still a symmetric measure, and the sign can always be ignored when using dichotomous nominal data. And that comes from this website. It's statisticssolutions.com. Take a look at it. It's a pretty good website if you're having trouble understanding some of the concepts in statistics sometime, or you want to learn something on your own that we didn't cover in class. Going to statisticssolutions.com is a good place to experiment on your own. So let's talk about analysis of variance as opposed to t-tests. All right, remember that t-tests are used to assess whether means between two groups are different, or whether the means or the averages between two groups are different. Okay, give me an example of that, you say. All right, well, how about males versus females, or Democrats versus Republicans? Let's say that we want to measure the males versus males who voted for President Obama versus the females who voted for President Obama. And is the mean of those groups different? Okay, Democrats versus Republicans, UNH students versus Southern Connecticut State University students. Both the t-test and ANOVA use sample data to test hypotheses about population means. Okay, what does that mean? That means that we're using data in samples that we collect, because we can't test a whole population, it's too huge, so we test samples to test hypotheses about populations. Okay, ANOVA can be used to compare means between more than two groups. Okay, t-tests could only be used to compare two groups. And this is the formula for the t-test. If you recall, t equaled the difference observed between sample means divided by the difference expected by chance. Okay, you didn't have to do that. That was done in SPSS, but that's what SPSS was doing to figure out the t. With ANOVA, we're using the F statistic rather than the t statistic. Okay, and if you look up on top, the t again was the difference observed between sample means divided by the difference expected by chance. With ANOVA, F equals the variance, or the differences between sample means divided by the variance expected by chance. Okay, so it's not just difference, it's differences, the plural. So in the formula for ANOVA, the comparison is based on variances rather than means, okay? And that's how we come up with the term analysis of variance, or ANOVA. And why is it based on variances rather than means? Because in a t-test, we have two sample means, and you could compute a sample mean difference, all right? Here's an example. Let's say we have mean 1 is equal to 20 and mean 2 is equal to 30. All right, it's easy to determine that you got a 10-point difference between the two sample means. Okay, there's 10 points difference. But what do you do if we add a third sample mean, like with 35? So we have 20, 30, and 35. Then the concept of sample mean difference becomes kind of difficult to define, because which one are we comparing? So the sample variance, however, is linked to sample mean. And small mean differences equal small variance. And large mean differences equal a large variance. And just like in the t-test, we could either use independent measures versus repeated measures, ANOVA, okay? And we're going to focus on independent measures. And how do you generate a hypothesis with ANOVA? Well, same as always. Right? There's no difference in the way that we do this in any other test. All right, the null hypothesis means that there's no difference in the means between the various groups in the population. The mean of the first group is going to equal the mean of the second group, is going to equal the mean of the third group, or it's going to be very, very close. Okay, the alternative hypothesis means that there is at least one population that does have a different mean than the other populations. Okay, here's some examples of null hypotheses. Crime rates are similar in the U.S., Australia, and Spain. Okay, all three are similar, so just go back up here, and what did I say is that mean 1, mean 2, mean 3, in this case, mean 1, mean 2, mean 3 are the same. So that's the null hypothesis, okay? Null hypothesis. And another example is there is no difference in the starting salary of UNH, John Jay College, and Eastern Kentucky University criminal justice students after graduation. Okay, the alternative hypothesis is that one of them is going to be different, or one or more of them is going to be different. And another example of a null hypothesis is that the average number of incarcerated individuals is the same in New York State, Texas, California, and Tennessee, whereas we know that they're actually higher in Texas. So that would be the null, but that would be the alternative. The null would mean that they'd all be the same. Okay. Research question: are the means between the groups of the independent variable different enough to have occurred by chance? Okay, or are they significant? Okay, now let's talk about factors and levels for a minute, because you're going to have to know about these, and you read about them in Graviter and Wallnow. Okay, in ANOVA, the variable that designates the groups being compared is called a factor. Got that? In ANOVA, the individual conditions or values that make up a factor are called the levels of the factor. And you're saying, DeCarlo, what does that mean? I mean, it's hard to understand. Well, let me give you an example. Let's say that we're looking at the starting salaries of University of New Haven, New York University, and John Jay College students. Okay, what's the factor and what's the level? Okay, the factor is the salary. The level is the money assigned to each group. All right, $60,000, $75,000, and $50,000. These are the levels of the factor. Okay? That's all it means. Nothing complicated here. All right, let's take a look at this. This is important to try to get your brains around. So I'm going to use my pen. And this is sample 1, sample 2, and sample 3. And each one of these, if you notice, we're looking at test performance across temperatures. In other words, do you take tests better when it's cooler or when it's hotter, or when it's kind of like a comfortable in the middle temperature, okay? So that's what we're looking at. So we're looking at an experiment examining learning performance under these 3 temperature conditions. Okay, we have 2 things that we're looking at. These, see this? This is all within one treatment. Okay, this is treatment 1, and it's all at 50 degrees. So these 5 people, 1, 2, 3, 4, 5, each got these scores. Okay, and the mean is 1. So the within treatments variance is the variability between these 5 people, whereas the between treatments variance over here is the data due to general differences in the treatment conditions or groups. Okay, so that's the difference, and we're going to use the means here. Mean 1 is different than mean 4 is different than mean 1 for treatment 3. Okay, so these are between. Okay, these are between, and these are within, between. Okay, so that's important to know. There are always 2 possible explanations for the difference or variance, because this is analysis of variance, that exists between treatments. Okay, the first is the actual difference, and what do I mean by the actual difference? Well, if you looked at that last experiment, the actual difference was the temperature. It was 50, 70, and 90. Okay, those were the actual differences. Now, what else could affect those numbers? Well, chance. Okay, either because of individual differences. So you may have had, like in that first group, there may have been smarter people than in group 3 or group 2, or there could have been younger people in group 1 and older people in group 2, or people that studied in group 3 and didn't in group 2 and 1. So that introduces other variables that aren't what we're measuring, because we're measuring temperature. And then the other thing could be experimental error. Let's say we got 3 thermometers, okay, and they read, this one reads, this is 2 degrees off, this is 1 degree off, and this is right on the money, okay? So it's going to give us mismeasures, so that's experimental error or error in measurement, okay? So that is something else that could affect our data. The F ratio. Okay, here's a whole bunch of numbers for you. You don't have to worry about these numbers, because what's going to do this? SPSS is going to do this. But let's take a look. Don't forget, F equals the variance between sample means divided by the variance expected by chance, which is the error term. Or F equals the variance between treatments or groups divided by the variance within treatments or groups. Or F equals the differences, including any treatment effects, divided by the differences with no treatment effects. You kind of getting the gist of this? Or F equals the treatment or group effect plus the differences due to chance divided by the differences due to chance. Okay? So let's take a look at what I mean here. The independent measures analysis of variance partitions, it lumps together or analyzes the total variability into two components: variance between treatments and variance within treatments. Okay, so within treatments, remember, think of those three groups again, and the differences between the groups. Okay, so the total variability has to do with between treatments variance, measures differences, and that measures the difference due to treatment effects and chance, and within treatments variance, because remember the temperature was all the same in that first group, second group, and third group, that measures differences due to chance. Okay, so both of those together gives us the total variability. Okay, and F ratio with no differences means that we fail to reject the null hypothesis. Okay, and treatment or group effect plus the differences due to chance divided by differences due to chance. All right, so what does that mean? You're going DiCarlo, you're confusing me. All it means is that if the numerator and denominator have the same values, the F ratio should have a value of about 1. Why? Because if you're dividing 6 by 6, 6 into 6 goes 1 time. All right, 7 into 7 goes 1 time. You get it? It's not complicated. When the treatment effect is 0, it means there's no difference between the sample means, then F equals 0 plus the differences due to chance divided by the differences due to chance. Okay, and what does that mean? An F ratio close to 1 suggests that differences between groups or conditions, which is the numerator, are about the same as differences expected by chance, which is the denominator. Okay, and when differences are observed, we reject the null hypothesis. Okay, when the treatment does have an effect, there's a difference between the sample means. So each one of those are going to have different sample means. And when the differences between treatments or conditions, the numerator should be larger than those due to chance, which is the denominator. Okay, so in that case we have a F ratio larger than 1. Okay, so if we're going to reject HO, we're going to have something larger than 1. Like for all the other tests we have used so far, a large F ratio indicates that the differences between the samples are greater than expected by chance. In other words, they're statistically significant. What the heck is the error term, you're saying? Well, the error term, remember, this is the formula for F, and the error term, the denominator in this formula, is also referred to as the error term, or chance. Okay. The error term measures the amount of error variability in the data for which there is no systematic or predictable explanation. Okay, so if we look at here, the differences due to chance, the treatment effect and differences due to chance, you remember the differences within groups? Okay, well, those differences are by chance. If they were all in the same experimental condition, then they are by chance. Okay, and that's the error term. The error term is used to determine whether the differences between groups are greater than would be obtained based on just chance alone. Okay, so we need to know what the error term is, and this is the way that it's figured. Okay, the degrees of freedom, in an F table we have to look up both of them. Okay, so this is the way it works. The degree of freedom total, n minus 1, all right, and what am I saying here? N equals the total number of observations, including all groups. All right, the first part of it is the degrees of freedom between the treatments, are k minus 1, and k is the number of groups, so it's just the number of groups minus 1, and the degree of freedom within treatments. So this is between treatments and within treatments, and this is the sum times n minus 1 equals n minus k. All right, so that's the total number of observations. Don't forget, SPSS is going to do this for you. I'm just giving you the theory behind it. The distribution of F ratios. Well, they're kind of like chi-square. It's the same principle as chi-square distributions and t-distribution tables. Okay, two things that you need to take into account about F ratio distributions are that, number one, because the F ratio is computed from two variances, F values will always be positive. Okay, and when the null hypothesis is true, the numerator equals the denominator. Okay, and that gives you 1, right? Which we were talking about before. If it's greater than 1, that means that what? Yes, go ahead and tell me. That's right. And so the structure and sequence of calculations for analysis of variance goes like this. And you can see this in your book also. The final goal for the analysis of variance is to get an F ratio, okay? And so F equals the variance between the treatments divided by the variance within the treatments, okay? Each variance in the F ratio is computed as a sum of squares divided by a degree of freedom. Okay, so the variance between treatments equals the sum of squares between divided by the degree of freedom between. The variance within treatments is the sum of squares within divided by the degree of freedom within. Okay, so to obtain each of the sums of squares and degrees of freedom values, the total variability is analyzed into the two components. The sum of squares total is made up of the sum of squares between and the sum of squares within, and the degree of freedom total is made up of the degree of freedom between and the degree of freedom within. Okay, here's a reminder. This is important. Measurement level requirements for mean test. What do we need? Let me get my pen here because this is really important. We need the dependent variable. It has to be an interval variable. And the independent variable can be nominal or ordinal, okay? So the independent variable is not the one, what happens? Is that the one that we're controlling or the one that we're not controlling? So let's say we're controlling the heat, okay? If we're controlling the heat and we turn it to 50 in that 50 degrees Fahrenheit, okay? That is our independent variable. And the dependent variable is the test score. Okay, test score is going to be our dependent variable. So the independent variable can be nominal or ordinal, okay? Whereas the dependent variable must be an interval. Okay, these are the postulates for mean test. They have to have independence of groups. They have to have normal distributions, and they have to have homogeneity of variance between the groups. Okay, variance equals the measure of spread around the mean. Homogeneity of variance equals the spread around the mean that must be similar between the groups. Okay, so you don't want to, with Levine's test, we have the null hypothesis, we have the alternative hypothesis. Which one do you want in Levine's test? We want the null hypothesis to be true because we do not want the homogeneity of variance assumption to be violated. All right, so we want them to be the same, no differences. What happens when we fail to respect the homogeneity condition, the Levine test? Well, it's not such a big deal if the sample sizes are about the same, okay, about the same size, for instance, as males and females. But if the sample sizes aren't near equal, then we have to refer to the following tests, which offer an alternative, the Brown-Forsyth and the Welch, okay, because they deal better with sample sizes that aren't equal. Okay, if we do violate, remember in the t-test we got to use the second line if we violated the assumption of homogeneity. Well, with these we go to the Brown-Forsyth or the Welch in ANOVA. Okay, summary. T-test and F-test. Mean test are used to assess whether the means between one or more groups are significantly different. That is, different enough not to be attributed to chance. All right, T-test for comparisons between two groups, and F-test are for comparisons between two or more groups. All right, in summary, the F statistic is the between group variance divided by the within group variance. If the variance between the groups is considerably larger than the variance within the groups, then the F ratio will be higher. All right, the differences between means are unlikely to be due to chance. The results will be statistically significant. All right, so here are some questions for you. The question is, ANOVA is a statistical procedure that compares two or more treatment conditions for differences in variance. Is that true or false? It's false. Why is it false? Because ANOVA uses variance in the computations. The purpose of the test is to evaluate differences in means between the treatment or conditions. So we use variance to compute the differences in the means, but it still evaluates the means. But we use an analysis of variance to get the differences between those means. Got it? Okay, here's another question. In ANOVA, the total variability is partitioned or chunked into two parts. What are those two variability components called, and how are they used in the F ratio? You remember? Well, they're called between groups and within groups. Between groups variability is the numerator of the F ratio, and within treatments variance is the denominator. Here's another question. In ANOVA, what value is expected on the average for the F ratio when the null hypothesis is true? What happens when the null hypothesis is true? The number on the top is going to be the same as the number on the bottom. I gave you an example. 6 divided by 6 is 1. All right, so when the null hypothesis is true, the expected value for the F ratio is 1 because the top and bottom are the same. They're measuring the same variance. Another question. What happens to the F ratio if differences between the groups get bigger? What happens to the F ratio if differences within the group are increased or gets bigger? Okay. Well, as differences between groups increase, the F ratio will also increase. As variability within the group increases, the F ratio will decrease, and that's how you get. You remember, we're using the variance to compute the differences in means at the end, and it's just simply changing that numerator and denominator. All right, so the F ratio is going to decrease because what the denominator is going to be bigger. And that is it for this week. So if you have any questions, let me know, and we will go ahead from there. And good luck with ANOVA, and we will continue our studies in statistics, and I hope everyone is enjoying the class.